In the 9th century, somewhere in the mountains of Sichuan or Shanxi province in China, a group of Taoist alchemists were trying to do something that had absolutely nothing to do with warfare. They were trying to live forever. Convinced that the right combination of minerals could produce an elixir of immortality, they spent years mixing, heating, and experimenting with whatever substances they could get their hands on, following recipes passed down through generations of mystical and medicinal tradition. At some point, one particular batch combined 3 ingredients: saltpeter, charcoal, and sulfur. And instead of granting eternal life, that mixture did something considerably more dramatic. It exploded. There are accounts of singed beards and burned down workshops scattered through the early historical record, which tells you everything you need to know about how that first encounter actually went. Nobody in that room was trying to invent a weapon. They called the resulting substance Huo Yao, meaning fire medicine, a name that still carries the faint, slightly embarrassing memory of its original purpose as a failed pharmaceutical rather than a future engine of conquest. And yet that one accidental beard-singeing batch of failed immortality medicine eventually became the single most consequential chemical discovery in the history of human conflict, the seed from which every gun, every cannon, and eventually every firearm on Earth would grow. So how did humans get from a failed potion in a Taoist alchemy lab to the firearm? The answer takes us through bamboo tubes strapped to spears, a siege that proved the new technology actually worked. Several centuries of careful refinement and a slow, steady migration of knowledge across an entire continent that eventually reshaped the balance of power on every inhabited landmass on Earth. Let's start with what that early gunpowder mixture actually was, in the simplest possible terms, because understanding the basic chemistry helps explain why everything that followed happened the way it did. The mixture those alchemists stumbled onto combined potassium nitrate, known as saltpeter, with charcoal and sulfur, in roughly a 75 to 15 to 10 ratio by weight. The saltpeter functioned as an oxidizer, meaning it released oxygen rapidly when heated, feeding an extremely fast combustion reaction that produced a sudden, violent expansion of gas. That expanding gas is the entire secret behind everything gunpowder would eventually be used for, whether that meant launching fireworks into the night sky or eventually launching a metal projectile out of a tube with enough force to punch through armor. In its earliest documented uses, gunpowder wasn't weaponized at all. It was used for fireworks, smoke signals, and festival entertainment, exactly the kind of celebratory, decorative application you'd expect from something originally discovered by monks chasing immortality rather than military engineers chasing battlefield advantage. For generations, ordinary people across China encountered this substance primarily as spectacle rather than threat, lighting up festivals and religious ceremonies with bursts of color and noise that had nothing to do with combat at all. That changed once military commanders during the Song dynasty got a look at what this volatile new substance could actually do. Between the 10th and 12th centuries, Chinese engineers developed something called the Huo Chia, or fire lance. And the design was genuinely about as simple as a weapon could possibly be. Take a length of bamboo, strap it firmly to the end of a spear, pack the tube with gunpowder, and light it during close combat. The result was a polearm that spewed flame and burning debris directly at anyone within arm's reach, turning an ordinary spear into something considerably more terrifying to face in a melee. Defenders used fire lances during the siege of Daean in 1132 against attacking forces climbing their walls, and by every account, the weapon worked exactly as intended, scorching and disorienting attackers in a way conventional spears simply couldn't match. The psychological effect alone was significant. Soldiers who had spent their entire lives training to fight with blades and spears suddenly found themselves facing an enemy who could project fire itself, and that kind of shock often mattered as much on a medieval battlefield as the actual physical damage inflicted. Once gunpowder had proven itself useful in actual combat, the pace of innovation accelerated quickly, and each successive improvement followed a fairly logical, almost obvious next step from whatever came before it. Makers of fire lances began stuffing pellets and shards of pottery into the bamboo tubes alongside the gunpowder, transforming a weapon that simply produced flame into one that also flung small projectiles outward with real force. This was a genuinely significant conceptual leap, because it shifted the weapon's purpose from pure intimidation and burning toward actual physical, penetrating injury delivered at a distance, the foundational concept underlying every firearm that would eventually follow. The next major limitation was the bamboo itself, which simply couldn't handle the pressure that more powerful gunpowder charges generated, without splitting or bursting apart in the user's own hands. occasionally injuring the very soldier wielding it. Once Chinese craftsmen learned to cast bronze tubes strong enough to contain that pressure safely, the hand cannon was born, a weapon that used the expanding gas from gunpowder combustion to launch a single solid projectile with considerably more force and considerably more range than any bamboo fire lance ever could. By the 13th century, metal-barreled hand cannons were already in regular use across China, representing a genuine technological leap in both reliability and effectiveness compared to the earlier bamboo-based weapons. Chinese engineers also scaled the same basic concept upward, producing devices with names like the thunderclap bomb and the heaven-shaking cannon, weapons capable of delivering genuinely high-impact explosions on a battlefield and reducing fortified positions that had previously seemed unassailable. When the Mongols invaded China in the 1200s, they encountered these gunpowder weapons firsthand during sieges like the famous defense of Kaifeng in 1232, and the experience left a lasting impression. Rather than simply being defeated by the new technology, the Mongols absorbed it, and once they had conquered China and established the Yuan dynasty, they carried gunpowder weaponry with them as they pushed westward into new conquests across Asia and toward the Islamic world. This is genuinely one of history's more important and underappreciated technology transfers, because Mongol military campaigns functioned almost like an accidental delivery system, carrying gunpowder knowledge across enormous distances far faster than trade caravans or diplomatic exchanges ever could have managed on their own, spreading a Chinese invention across the breadth of Eurasia within the span of just a few generations. It's also worth noting that gunpowder weapons didn't develop along a single straight line during this period. Alongside hand cannons and fire lances, Chinese military engineers also developed rockets and fire arrows, gunpowder-propelled projectiles that found use not just in China but eventually in Korea and India as well, traveling along separate but overlapping routes from the hand cannon's own path westward. These rocket weapons never fully disappeared the way the fire lance eventually did once true guns matured. Instead, they persisted as a distinct branch of gunpowder technology, one that would resurface centuries later in European warfare. And, much later still, in the earliest ancestors of modern military and space rocketry. The story of gunpowder, in other words, doesn't just lead to the gun. It branches with one path heading toward the firearm and an entirely separate path heading toward the rocket, both rooted in the same accidental discovery made by alchemists who wanted nothing to do with either outcome. From there, gunpowder technology spread outward along multiple overlapping routes simultaneously, reaching the Islamic world and eventually Europe through a combination of military contact, trade, and the broader wave of cross-cultural exchange that characterized the 13th and 14th centuries. Historians studying this period point to a broader pattern worth appreciating. Gunpowder wasn't the only major Chinese invention making its way westward during this era. Paper, printing, and the magnetic compass all traveled the same general routes during roughly the same stretch of centuries, part of a much larger flow of technology and knowledge moving from east to west long before anyone had coined the term globalization. Some historians have noted that early European cannons bear such a close structural resemblance to Chinese designs that a direct transfer of knowledge seems considerably more plausible than independent invention happening to arrive at nearly identical solutions by coincidence. Once the technology reached Europe in the late 13th century, it landed in a political and military landscape that gunpowder weapons would, over the following centuries, completely and permanently transform, eventually dismantling systems of feudal military power that had stood for hundreds of years. The transformation wasn't instant. Early European hand cannons, much like their Chinese predecessors, were crude, slow to reload, and difficult to aim with any real precision. Essentially, a small cannon mounted awkwardly on the end of a pole. You loaded powder and projectile into the open end, touched a smoldering ember or a length of slow-burning cord to a small touch hole, and hoped with considerably more optimism than confidence that the resulting explosion would actually send the projectile somewhere useful. But even in this primitive form, the weapon carried a psychological and practical impact that traditional melee weapons simply couldn't match. Castle walls that had withstood traditional siege equipment for generations began falling to cannon fire. Mounted knights in heavy armor, the dominant military force across medieval Europe for centuries, found themselves increasingly vulnerable to a weapon that didn't care how much steel you were wearing, since enough gunpowder-driven force could punch straight through it regardless. The entire social and military order built around expensive, heavily armored cavalry began to wobble because a relatively cheap weapon in the hands of a far less expensively trained soldier could now neutralize an opponent who had spent a lifetime and a fortune preparing for combat in the traditional way. This shift had consequences far beyond the battlefield itself, reshaping the very architecture of European warfare. As cannons grew steadily more powerful and increasingly effective against vertical stone walls, traditional castle design, built around tall, thin walls meant to repel scaling attackers and arrows, became dangerously obsolete almost overnight in historical terms. Military engineers responded by developing the Star Fort and the Bastion, lower, angled, thickly reinforced fortifications specifically designed to deflect and absorb cannon fire, rather than simply standing tall and hoping for the best. The medieval castle, an architectural form that had dominated European landscapes for centuries, was gradually replaced by structures that looked almost nothing like it. All because of a weapon that had originated half a world away in the hands of monks chasing immortality. The next genuinely important leap came in the late 15th century with the invention of the matchlock mechanism. And this single development is what finally turned gunpowder weapons from clumsy novelties into the backbone of organized infantry warfare across the continent. The fundamental problem with earlier hand cannons was that actually firing one required two hands and considerable coordination. One hand to steady the weapon, the other to apply a burning ember or cord directly to the touch hole at exactly the right moment, all while trying to actually aim at a moving target on a chaotic battlefield. The matchlock mechanism solved this elegantly by attaching a slow-burning cord held in a curved clamp called a serpentine directly to the weapon itself. Pulling the trigger lowered that already burning cord directly into a small pan of priming powder, igniting the main charge automatically and freeing the shooter to actually hold and aim the weapon with both hands, right up until the moment of firing. This may sound like a modest mechanical tweak, but it was genuinely transformative because it was the first mechanical firing device ever applied to a small arm, and it allowed, for the first time in history, a single trained soldier to fire a gunpowder weapon with some real degree of aimed precision rather than simply pointing roughly in the right direction and hoping for the best. By the early 15th century, matchlock arquebuses were appearing in growing numbers across Western Europe, particularly in Spain, France, and the territories of the Holy Roman Empire, and the weapon spread rapidly from there across the entire breadth of Eurasia. The Ottoman Empire, already experienced with gunpowder weaponry since the 14th century, incorporated matchlocks directly into the elite Janissary Corps that formed the backbone of Ottoman military power, using the weapon to great effect in engagements such as the Battle of Goa in 1510, alongside the Portuguese forces that also relied heavily on matchlock weaponry during that same period. In 1543, Portuguese traders introduced matchlock technology to Japan, where local gunsmiths refined the design so thoroughly that Japanese matchlocks, known as tanegashima, came to be regarded as some of the finest crafted firearms anywhere in the world during that period, prized for their precision and craftsmanship even by European observers. China itself, having started this entire chain of innovation centuries earlier, ended up reabsorbing an improved version of its own original invention, developing matchlock weapons known as birding guns, specifically to counter ongoing Mongol incursions along its northern frontier, a genuinely strange and fitting historical loop for a technology that began as a failed immortality potion in that same general region. Matchlock muskets eventually became heavy, powerful enough to need a forked rest just to support the barrel while aiming, weighing as much as 25 pounds in some configurations, but capable of punching through plate armor at ranges that made traditional swords and pikes increasingly irrelevant on an open battlefield. Because reloading and firing a matchlock took considerable time, and because the weapon left the user briefly vulnerable during that process, musketeers typically required protection from melee attacks, usually provided by pikemen standing alongside them. This combination of pikes and shot came to dominate European battlefields from the 16th into the early 17th century, an elaborate, carefully choreographed tactical system requiring extensive training to coordinate effectively, with musketeers firing from behind or between rows of pikemen in tightly organized formations. Outside Europe, many armies that had adopted matchlocks retained their traditional formations rather than developing this same dense, disciplined infantry coordination, lacking either the resources or the specific tactical incentives that drove European armies toward this particular evolution in organized combined arms warfare. The matchlock had one obvious, persistent weakness that everyone using it understood immediately. It required an open, slow-burning flame at all times, which made it nearly useless in wet weather, gave away a soldier's position in darkness, and required constant management of burning cord even when nothing was happening on the battlefield at all. The solution arrived gradually, through several intermediate steps worth understanding. The wheel lock, developed in the early 16th century, used a spring-loaded wheel spinning rapidly against a piece of pyrite to generate sparks, eliminating the need for a constantly burning match entirely. This made wheel locks considerably more practical for cavalry who needed a weapon they could carry loaded and ready without tending an open flame while on horseback. And German mercenaries along with English cavalry units became particularly associated with this mechanism during the 16th and early 17th centuries. But wheel locks were expensive and mechanically complex to manufacture, which kept them from ever fully replacing the cheaper, simpler matchlock among ordinary infantry who continued carrying the older, more affordable design well into the following century, even as wealthier cavalrymen rode with the more advanced alternative. The true breakthrough came with the flintlock, generally credited to French gunsmith Morin Le Bourgeois, who developed the mechanism in its recognizable modern form around 1610 to 1615. The flintlock used a spring-loaded hammer holding a piece of flint which struck a steel surface called a frizzen to generate sparks directly into the priming pan, igniting the charge. It was faster to operate than a matchlock, dramatically more reliable in poor weather, and required no open flame to maintain at all, which also meant soldiers no longer gave away their position in the dark simply by carrying a lit weapon. By the 1630s, the flintlock mechanism had spread rapidly across Europe, with the Dutch States Army among the first to formally adopt it as a standard-issue infantry weapon, and within a few decades it had become the dominant firearm mechanism across essentially every major European military, a position it would hold for roughly 2 centuries, right through the colonial expansion, the Napoleonic Wars, and the American Revolution that followed, where flintlock muskets carried by both colonial militias and British regulars defined the entire conflict from start to finish. The flintlock's arrival coincided with another genuinely important innovation, the socket bayonet, introduced in the late 17th century, which attached around the outside of the barrel via a metal ring rather than plugging directly into the muzzle the way earlier plug bayonet designs had, which rendered the gun unable to fire while the bayonet was actually attached. This seemingly small change meant a soldier could fix a bayonet to his musket and still fire it normally, combining ranged firepower and close combat capability in a single weapon for the first time. The practical effect was enormous. Armies no longer needed dedicated pikemen standing alongside their musketeers for protection, since every soldier carrying a flintlock and bayonet could now function as both shooter and spearman, depending on what the moment required. This single combined development, sometimes called the infantry revolution, simplified training, simplified logistics, and fundamentally reshaped how European armies organized themselves on the battlefield, allowing regiments to become more versatile and capable of engaging enemies at range or in close combat without needing to reorganize entirely between the two modes of fighting. The bayonet charge also carried its own distinct psychological weight on the battlefield, since the sight of an advancing line of soldiers with fixed bayonets often broke enemy morale before a single shot or thrust ever actually connected. The flintlock's roughly 2-century reign finally ended in the early 19th century with the arrival of the percussion cap system, a small metal cap containing a shock-sensitive chemical compound that ignited instantly when struck by a hammer, eliminating the need for loose priming powder, flint, and steel entirely. This final ignition innovation rendered every previous mechanism, matchlock, wheel lock, and flintlock alike, essentially obsolete within a few decades, and it marked the last major milestone in the centuries-long chain of refinements that had begun with monks chasing immortality in 9th century China. From there, the pace of change only accelerated, leading toward repeating rifles, rapid advances in metallurgy and manufacturing, and eventually weapons that would have been utterly unrecognizable to the soldiers who once stood in disciplined lines with pikes and matchlocks, waiting for their turn to fire. Looking back across this entire arc, from a Taoist alchemy lab in 9th century China to flintlock muskets dominating European battlefields nearly 8 centuries later, the story of how humans invented guns is really a story about accident, accumulation, and migration happening together over an enormous span of time. Nobody set out On day one, to invent the firearm, a group of monks looking for immortality stumbled onto an explosive chemical reaction and very nearly burned their own beards off in the process. Military engineers watching that explosive reaction gradually realized its violence could be channeled, first through a tube strapped to a spear, then through a cast bronze cylinder, then through increasingly sophisticated mechanical systems designed to ignite that same basic chemical reaction more reliably, more quickly, and with less risk to the person holding the weapon. Each individual improvement, the shift from bamboo to bronze, from open flame to spring-loaded mechanism, from matchlock to flintlock, addressed a specific practical problem that soldiers and engineers had actually encountered using the version that came before it. None of it required some singular genius moment of total invention. It required centuries of incremental refinement, carried across continents by trade routes, military campaigns, and the kind of slow cultural exchange that quietly reshapes the world while nobody's watching closely enough to notice it happening in real time, passing hands between Chinese engineers, Mongol conquerors, Ottoman janissaries, Japanese gunsmiths, and European craftsmen, each group adding their own refinements along the way. The gun that would eventually end the dominance of mounted knights, reshape castle architecture, and ultimately determine the outcome of colonial conquests and continental wars across multiple centuries began its existence as a mistake made by people who were never trying to build a weapon at all, looking instead for something considerably more peaceful, a way to live forever.